So continuing on with this example, again, we've established that I've been given a pressure value and I've been given a specific volume value. So I'm going to draw a PV diagram to figure out my phase, right? Because I've gotten to this point. I need to determine my phase so I know which table, which row, because I need to know the temperature and I also need to know the phase, okay? So, drawing a PV diagram, it doesn't have to be pretty, it doesn't have to be exact, it just needs to be a rough shape. Okay, so I'm going to go look, given 20 psi A, I'm going to go look up and see where these values are. This is my this is my VF value and this is my VG value. No, I've switched those. I apologize. This is my VF value and this is my VG value. Okay? So we go look in tables, and I happen to have scanned these in. I hope you can see that fairly well. What kind of glare am I getting on that? Oh, good. I've got the angle about right. So what do I got here? Give me my... So I know at 20 psia, so I'm going to set this down. I can't draw it there, but I can pick it up after I've drawn here. So I know at 20 psia, take a straight edge or a ruler and put underneath that so you just see the one row that's important there. And so notice at 20 psia, right, so again I've got water, so go find water tables in the English units. I'm given a nice round value of pressure, so go to the pressure table. That would be table A5. A4 has nice round values of temperature. I have a nice round value of pressure, so I'm going to go to table A5. And then put your straight edge and go across here. And what other property we have? Well, we have volume. So I go across here and see where am I at volume. I match this one exactly, which doesn't normally happen, by the way. And we're going to talk about what do you do when it doesn't match. But here's what we've got, right? We've hit this point right here. Our VG value is 20.093, and that is our V value. So that tells us that our phase is saturated vapor because our V value is equal to the VG value. Our specific volume is equal to the value for saturated vapor. So our phase is saturated vapor. Okay? Our temperature then, because it's saturated anything, it's at the boiling point, right? So if it's anywhere on this table, that means it's somewhere in here, and that means it's boiling right now. So if it's boiling, that means the pressure and the temperature values are locked. So at this pressure, it boils at 227.92 degrees Fahrenheit. That becomes our temperature, 227.92 degrees Fahrenheit. And these are our answers. So we'll just underline them or box them in, and that problem's done. Okay. So, if you have a specific volume greater than the value for your saturated vapor, that puts you in the superheated vapor region. We've drawn these diagrams earlier, right? So if I found my V value put me out here, that puts me out here in the superheated vapor region, right? Or if I've got a V value that puts me behind the VF value, if I've got a V value that puts me back in here, that puts me in the compressed liquid region. And that's what we're saying here. So if my given specific volume or U value or H value or S value is greater than the value, the corresponding value for saturated liquid, or sorry, saturated vapor, that puts us in the superheated region. And the same thing for compressed. If it's less than the value for saturated liquid, that puts you in the compressed liquid region. Okay? So let's look at this one here. Similar example, very similar setup. Okay, let's write this one down. Another example. Okay. Given, I've got water. I've got, again, a pressure of 20 psia. And I've got another kind of very specific volume value. They're not normally that detailed, but this one is 22.98 cubic feet per pound mass. And again, they want us to find the temperature and the phase. Okay. So again, we go look at our process and say, all right, how do we do that? Well, they want me to find the temperature. That's a property, so I'm going to go look it up in the property tables. Well, I've got two properties. So I know I've got water. I've got two properties. I've got pressure and volume. Determine the state. So go find which table, which row. Okay, so I need English unit tables. I've got English units, so English unit tables. Go determine the phase. To determine the phase, again, I'm given a pressure and a volume. So PV, roughly draw the diagram. Where do I fall in relation to the G and the F values? Well, remember last time, we already looked this up. At 20 psi-A, the specific volume for saturated vapor was 20.093. And if we hadn't just done it, you can go look at the tables and know at 20 psi-A, water is going to have a specific volume in saturated vapor form of 20.093. So where are we at? Well, we got 22.98. That puts us out here. 22.98, that puts us out here in the superheated vapor region. That means I need to go forward into the superheated vapor tables. So that's table A6 here. Alright. Alright, I've got a block down here of 20 psi-A. Alright, 20 psi-A. And I've got a specific volume there of 22.98. So this is my block, my pressure block down here. Let's bring the pin up. Okay, everything's fine. No, give me ink back. There we go. So I'm in this pressure block. Okay. Now notice there's a temperature here in parentheses. That is the saturated temperature. That is the boiling temperature at that pressure. Okay. So there's a row here for saturated. This top row is the corresponding saturated vapor values. You could actually start in this table and see how you compare to those and work your way back. But in this case, we know we've exceeded the saturated vapor values, so we should be down here. Notice these values increase as you increase the temperature. Okay? So we look and see, well, again, I've got a specific volume, we said, of 22.98 right here. So you put a straight edge, or if you don't mind drawing in your book, that is one advantage of digital, is you could draw on it probably and then erase it if you have some kind of app that allows that. So I found a match at 320 degrees Fahrenheit. Right? We know, again, the phase is superheated vapor. How do we know that? Well, because I'm out here, so I had to go to the superheated tables to find it. And the temperature, this specific volume matches up perfectly with the corresponding specific volume at 320 degrees Fahrenheit. And so those are our answers. And if I'm in the classroom, I'm writing those answers here on this sheet. I've got them here, so there's no reason to write them twice for you guys. Okay. So if we draw this on one big PV diagram, okay, so we look and see how this thing looks. Okay, I'm going to set this one aside. I'm going to keep this one handy. So we draw the whole thing on one big PV diagram. I'm going to try to leave enough detail here. Okay. I'm just going to come out way far out here. Okay. So again, at 20 psi-A. Okay? And what I've got here, so if I go back and look at this table, so at 20 psi-A, no, 10, At 20 psi, I know I've got a temperature here of 227.92. So I know if I draw a line of constant temperature across here, we'll do a different color. A line of constant temperature is going to come across here at 227.92 degrees Fahrenheit. Okay? And that's going to intersect the saturated curve right here at 20.093 on my specific volume. That's cubic feet per pound mass. So we'll write it once, so we don't have to write it every time. Back over here, the saturated liquid value is 0.01683. I'm not making that up. That's here on the table. You can see right there. Okay. All right, and then you say, well, that doesn't match what we have. What we have is over here at 320. I've got 22.98. And so I come out here to 22.98 degrees Fahrenheit. I'm sorry, not degrees Fahrenheit. 22.98 cubic feet per pound mass. And that's where this other one's at. And what I've got is I've got a line of 320 degrees Fahrenheit. And it's going to come across up here, something like that. Now, we didn't look up any of these other points, but we could go look, if you like. See if I can do this quickly here. Erase the clock. Just to plot more points. This is way beyond what the problem asked, but no, English units. So I've got my book here. I'm flicking through my book. Not doing it under the document camera because I feel like it'd be a little easier here. So 320 degrees Fahrenheit down here, I've got a pressure of 89.667. 89.667 is the corresponding pressure. 89.667 psi. That is the saturated pressure for 320 degrees. So if I drew my line of constant temperature for 320 across here, it would flatline through the saturated dome at 89.667 psi, way above 20. But that doesn't matter in this problem. Again, I know 20 psi and I know this particular specific volume. So we go look and see in the tables, right, where does that occur? Well, that occurs back over here at 320. Okay? All right. Now, what else we got? Okay. So the last thing to mention here is this other category. That's kind of this idea here, given a pressure and temperature. So if you're given a pressure and a temperature, if the temperature is greater than Tsat at the given pressure, you have a superheated vapor. If it's less than Tsat at the given pressure, you have a liquid. And what that means, and this is not the same example, this is another example. I guess we could use that same data, right? We could say that if I plot P and T here, okay, what I know is, let's say I know 20 psi. Well, I know the saturated temperature, I can go look that up, is about 228, and it's 227.92 degrees Fahrenheit. So what this is saying here is that if you go look up the saturated temperature at your given pressure, if your temperature is greater than that value, out here at 320, that puts you in the vapor region. And if you have a temperature less than this, it puts you back here in the liquid region. All right, we'll come back on that.